Hello and welcome to my very first YouTube video. I decided to make some YouTube videos about logic and type theory, which are going to use TypeScript as as a way of explaining stuff. This isn't because TypeScript is particularly suited to doing kind of heavy-duty formal mathematics, but on the other hand, it is the programming language I know the best, and I think it's also probably one of the most widely known languages that has any kind of type system. So I thought it would be fun to try to explain some classic things from logic, set theory, and type theory, which I'm also just in the process of learning some of these things myself, while illustrating it with some TypeScript, JavaScript code. Okay, so for my first video, I thought I'd do something relatively simple, and that's a presentation of Russell's paradox. We're going to do it. So Russell's paradox classically is a problem with something that is called the comprehension principle in set theory. And the comprehension principle says that for any property you can articulate about sets, you can have a set of that property. So if I say like the set of all sets with 5 members, I should be able to get that. If I say the set of all sets that have that don't contain the set that represents the number 5, I should be able to have that, and so on. And Russell's paradox takes a particular property, which is the set of all sets that don't have themselves as a member. And from this, it derives a contradiction. And this paradox was actually part of the reason why mathematicians abandoned what's known as naive set theory, which was being developed starting with Cantor and going up through Frege. And then they realized they had to do something a bit different if they wanted to avoid contradictions. So I'm going to explain this using the idea of an array of all arrays. So in JavaScript and many programming languages, you have arrays, which are essentially lists of elements. This first function here on line 2, array eq, is just defining a simple equality of arrays. So this is equality in terms of the value of the elements. And you'll see in my TypeScript types, I've just said that you're comparing any value to array 1. So the first element you know is an array. The second element might be an array or it might not be an array. If it's not an array, obviously it's not equal to the array, which is down here. You're returning false. And if it is an array, you compare every value. Now I like this as a relatively new method in JavaScript to have an every method on arrays, which allows you to basically do a for all predicate over arrays. Okay, so now we're going to get our set of all sets that are not elements of themselves, we're going to create what I call the self-reference filter down here on line 10. And so this, we're just taking any array as an argument. Oh, I'm sorry, any array of arrays. So you can see over here, we've got this double array symbol here. So this just means that the type is any arrays that contain, an array that contains arrays of any type. Actually, in some sense, that's the TypeScript way of defining the array of all arrays. Because it's an array that could have not the particular value. Of course, this R parameter will only ever be one particular array of arrays, but the actual type, any array, is in some sense abstractly representing the array of all possible arrays in JavaScript. So if we take this, but we're just going to act on a particular argument, obviously, because we can't act over that whole infinite type. So we're going to take that array. We're going to filter the members of that array such that if the member of the array is, if for every member of that array, its element is not array equal to itself, right? So that is, of course, if you were to actually try to have such a self-referential looping code, you might end up getting a non-terminating code, because you might end up kind of having infinite recursion. But we're not going to worry about that, because we're dealing with the sort of pure mathematical ideas, and we're only illustrating it with this code. This code is not actually meant to be run in a practical way. But basically what this does is it applies the filter and says that if that the element cannot be equal to the actual member array, right? So in other words, every array which is a member of our original array cannot contain an element, i.e. That's the third level nested now. So it cannot contain an element which is itself, right? So that's the sense in which the self-reference filter will filter, give it any array, and it will filter out arrays that are members of itself. So I've illustrated this here. You have to do this in 2 steps. First, you have to create the array. So we've created an array B. This is just an empty array. Now we can use the push method to push B into itself. And now we have an array that contains itself. So actually, there's no problem doing that in JavaScript or in most programming languages. You can have self-reference of that sort. And then similarly here, we have an array that contains B, and then we're going to push it into itself as well. So this is just to illustrate that it's not only direct self-reference, where B is directly a member of B, but also even if A contains B and B is a member of B, that is also something that will get filtered out by our reference filter. I think this A was meant to say cat. Just giving you examples of different values you might have inside an array. So our self-reference filter will not filter out any of these other values because none of them have members which are equal to themselves. But it does remove both the member A and the member B from our array A over here. We're applying it to A. So that's just to show you that there's nothing kind of wrong with this self-reference filter. I mean, there might be, if you actually try to run it, you might get non-terminating code. So that's obviously wrong from a practical perspective. But, in terms of just thinking of it mathematically, there doesn't seem to be anything inherently paradoxical or contradictory about this idea of a self-reference filter. In fact, in some ways, it's very straightforward. We're just removing elements that contain themselves as elements. And I think that's important because sometimes when you first hear about paradoxes, it can seem like there's some sort of sleight of hand or some sort of trick going on that, and I think I often felt that way in the past, that it kind of seems like I don't need to really worry about that. It seems kind of silly or like a parlor trick, as I said. But in fact, when you make it really concrete like this with the code, I think it helps to show you that actually there's a really strong sense in which it's at least the setup of it doesn't seem problematic. So now, of course, what are we going to apply our self-reference filter to? Well, we've so far just applied it to a couple of random examples of arrays. But if we want to actually get the set of all arrays that are not members of themselves, right? Because this, of course, applying self-reference filter to A or to B just gives us this particular array with its self-containing members removed. But if we wanted to get an array that has all of those arrays that don't contain themselves, what would we need to start with? Well, we'd need to start with what I'm calling here omega. Sometimes omega, the Greek letter, is used to represent infinity. Sometimes it's used to represent truth values. In this case, we're using it to represent infinity. So, or the totality maybe is a better way of saying it, because it's not just infinity, but it's a particular kind of totality. And in this case, omega is representing the array of all arrays, right? And here, of course, we have our type in TypeScript, which is in some sense already the array of all arrays, but you can't directly convert that type into an actual JavaScript value, because if you could, that JavaScript value would be infinite, and you can't actually have, at least in JavaScript, you can't have an infinite value. So that's why I've just kind of put this in quotes here, array of all arrays, right? So if you imagine that this is actually an array that contains every array, then we can move on with the next step. So now, of course, we're going to apply our self-reference filter to this omega. And you can ask yourself, well, what effect is that going to have? Now, if we ask ourselves about, and just important that I've called this, assigned this value, the result of applying the self-reference filter to omega, I've called that omega filtered. So first we can ask ourselves, is omega filtered an element of the array omega? Well, yes, it will be, because omega by definition contains every array, so omega filtered has to be in omega. All right, and so then we can say, does omega filter have itself? I'm just going to does omega filter have itself as an element? Well, the answer, again, by the definition of the self-reference filter, is no, because it's an array. It's the result of applying the self-reference filter, so it can't have itself as a member. So it's an element of omega, and it's not a member of itself. But since it's an element of omega and it's not a member of itself, then the self-reference filter is going to copy it, right? Because remember the way filter works, going back up to our definition of self-reference filter here, right? We're just using this basic JavaScript method filter, and what that does is it takes an array, it copies it, except it leaves out the members that return false from this callback function you pass in. So in this case, this is only going to return false for arrays that are members of themselves, right? And we've just argued that omega filter is not a member of itself because it is the result of applying self-reference filter. This is where the reasoning and logic gets a little twisty, but try to wrap your head around it. At least I find it difficult sometimes because of this twistiness. But the omega filtered, by the definition of self-reference filter, has to not have itself as a member. By the definition of omega, it has to be in omega. So therefore, the self-reference filter is going to preserve it and copy it into omega filtered, right? Because remember, it starts out in the original omega, and self-reference filter has no reason to filter it out, so it's going to put it in there. But now, boom, we get our contradiction. Because as soon as omega filtered ends up as an element of omega filtered, we've got that it's a member of itself, right? And if it's a member of itself, as we saw up here with A, now it's not actually a problem in the first level that it's a member of itself. It's the problem that any set which is a member of itself will also, as a member, have itself. So you have to go down to that third level. So omega filtered is an element of omega filtered, but as an element, that element also has itself in it because it's going to have omega filtered in it as many times down that chain as you want to go. So therefore, it should be filtered by self-reference filter, right? But of course, it's also the product of self-reference filter, and so it therefore can't have itself as a member. And then you keep going around in the circles, and that's the nature of most of these paradoxes, is you kind of get into this infinite loop of flipping the truth value, or in this case, flipping whether or not it's a member of itself back and forth. And that, in a nutshell, is Russell's paradox. So if you apply this same line of reasoning to the set of all sets, and you think about filtering that set of all sets with this property that says the set of all that says that you only take those sets that are not members of themselves, you get the same paradox, but in the land of set theory. So thank you. I guess if you like this video, leave comments, or I'd love to hear what you think of it. As I said, it's my first video, so it might have not been as I guess well made as it could be, and hopefully in the future I'll get better at doing this. And that's all for now.